So let's generalize a little bit. We're going to go from exponentials to something more general called gamma. And this is sort of, you probably want to think of this like geometrics generalizing to negative binomials. Remember we saw that negative binomials model the time until the rth success, right? So you can think of a negative binomial then as a sum of r geometric random variables, right? Because you have to see one success and then another and then another. Geometrics model the times between these successes. If you add up r of them, you get a negative binomial. Similarly, exponentials also model the time until the time between successes. You can think of them like that, right? Except in continuous time. So we can think of gamma random variables as, in a sense, they're more general. They're generalized exponentials. With the right parameter values, gamma random variables are actually sums of exponentials. So maybe if the times between bus arrivals to bus stop are exponential random variables, which they're probably not, but if they were, then the time until the 10th bus arrives could be viewed as a gamma random variable. Okay, so that's the connection there. So x, we'll say, is a gamma random variable with these parameters, alpha and beta, with alpha and beta greater than 0. Okay, we need that those parameters are greater than 0. If its density function looks like this mess, okay, x to the alpha minus 1 times e to the negative x over beta, all over beta to the alpha times gamma of alpha, where this gamma thing here is the famous gamma function. Okay, gamma of alpha is defined to be the integral from 0 to infinity of x to the alpha minus 1 times e to the negative x dx. Okay, this is the famous or infamous gamma function. Okay. Here is a fun fact. Fun fact. Gamma of alpha can be written as alpha minus 1 times gamma of alpha minus 1. And we can prove that here. Gamma of alpha is so this is, by definition, this thing is from the integral from 0 to infinity of x to the alpha minus 1 times e to the negative x dx, right? Now, there's this thing that we all love from calculus called integration by parts. Okay, I know from experience that maybe this would be a good choice for you, and this would be a good choice for me. No, just kidding. dv. Remember that? Remember how to integrate by parts? You have to pick one part of the integrand to be u and the other part of the integrand to be dv. Right? So this means that du can be written, right, if I think about differentiating this stuff with respect to x, it's alpha minus 1 times x to the alpha minus 2. But then I've either got to divide by dx over here or put the dx over there. We'll do that. Okay, and then now if this stuff is dv, then what is v? Negative e to the negative x, right? I know that because that's got to be right, because if I differentiate this stuff with respect to x, I get e to the negative x, right? Yeah, good. Okay, so again, so this is integration by parts. Remember when you asked your professor in calculus when you would ever use that, and they said, well, I don't know. Well, here you go. We just used it. Now, so this implies that gamma of alpha can be written as, well, this is, integration by parts, uv minus the integral of v du. right? More specifically, if I fill in for u and v and du and stuff, I get, let's see, my u down there, that I'm going to get negative x to the alpha minus 1 times e to the negative x, I think. And then take the difference of the limits as x goes to 0 and infinity, right? And then minus integral from 0 to infinity there of e to the negative x. Wait a minute, I need a negative sign in here, so I'm going to pull it out here and turn that positive. It's alpha minus 1, x to the alpha minus 2 dx, right? Okay. Now, this is where you got to be careful. If I substitute in 0 in here, I get 0 times e to the 0, which is 0. But if I put an infinity in here, I get, let's see, negative infinity to some power that's like infinity if this is bigger than 1, you know, and then this is going to 0, this is going to infinity maybe. I get like 0 times infinity. I don't know what that means. Remember, you have to think of this thing as the difference between two limits. You have to think of it that way. So I'm going to write this then as the limit, say, as x goes up to infinity of negative x to the alpha minus 1 e to the negative x. And then minus the limit as x goes down to 0, right, of the same stuff. Negative x to the alpha minus 1 e to the negative x. So all of this is just this first part. Then I have this integral here. This integral, I'm going to pull out the alpha minus 1, and just like those tricky physicists, let's be looking constantly for familiar forms, familiar things. Does this thing at all look familiar? Does this integral look familiar? Yes, it does. Sure does. It looks a lot like the gamma function, right? If I come back over here, this was the gamma function. Integral 0 to infinity, integral 0 to infinity. Got a x to the alpha minus 1, got a x to the alpha minus 2, it's different, e to the negative x, e to the negative x dx, okay? Yeah, so basically this is the gamma function over here. It's just, but it's not gamma of alpha. Instead of it, this stuff is gamma of alpha minus 1. Okay, so in fact, all of this together is the solution, right? Is our desired right-hand side. All of this is alpha minus 1 times gamma of alpha minus 1. All right, so that's what we're supposed to prove, that that it's equivalent to. So what I need to do now is I just need to show that these two limits, if I take the difference in these two limits, I get 0. So let me work with this one first because it's actually easier. Okay. I take the limit as x goes down to 0 of that stuff. What's the limit as x goes down to 0 of x to the alpha minus 1 e to the negative x? Well, the product of the limit of the product. The limit of the product is the product of the limits, right? Provided that everything, is okay, nothing's exploding. So, so what is the limit of x to the alpha minus 1? The limit, right? If I take this is just 0, right? And then what's the limit as x goes to 0 of this stuff, of e to the negative x? It's just 1, right? So it's 0 times 1, which is 0. Now I'm going to work with this part. This part is going to be a little trickier. In fact, it's so tricky, I'm going to move on to another piece of paper here. Take long, I promise. This is this is the limit as x goes up to infinity of say, x to the alpha minus 1 over e to the x, right? So another way to write that. Now, I'm going to remember a trick from calculus, Hopital's rule. Remember this? It says that the limit of the quotient is the same as the limit of the quotient of the derivatives, right? So if I take d dx of x to the alpha minus 1 over e to the x, I get, let's see, the derivative of the top with respect to x is just alpha minus 1 times x to the alpha minus 2 there, right? And then what's the derivative of e to the x with respect to x? It's just e to the x, right? So you know that the bottom didn't even change. And the top, I just, when I pull down the exponent and do that, the usual thing. What I want to do here is I want to apply L'Hopital's rule here several times. So apply L'Hopital's several times. So in fact, what I think I want to do here is I want to, whoops, I forgot my limit symbol, right? So I'm going to take the limit as x goes up to infinity, and I'm going to differentiate with respect to x in the numerator and the denominator, but I'm going to do it this many times, the floor of alpha. Okay, alpha might not be an integer. Okay. Now, if you don't know where I got that, maybe you should just think about differentiating it 5, 10, 100 times. See how many times you really need to differentiate. It doesn't really matter how many times we differentiate the bottom, right? We're always going to get the same thing. It's the top part that we need to differentiate so that we get something sort of small, something so that it's down below 0. So if I take the derivative of x to the alpha minus 1, in the top here, the floor of alpha times, what you end up getting is now, let's see. First of all, the bottom stuff here is just going to be e to the x, right? And then in the top, I'm going to have, alpha minus 1 comes down, and then I'll have alpha minus 2 comes down, alpha minus 3 comes down, and so forth. And I've got a bunch of stuff, a bunch of factors with alphas in it, multiply together. That's just some big constant k. All right? And then what am I left with in the top? I'm actually just left with x to the alpha minus the ceiling of alpha. Okay? Turns out. I'll let you meditate on that a little bit there. And then so what happens now as x goes to infinity? The bottom explodes, right? And what is alpha minus the ceiling of alpha? If alpha is greater than 0, remember alpha and beta, the two parameters have to be greater than 0. If I take something like, if alpha is like 5.5, and I subtract the ceiling of alpha, which is 6, I get some small number that's it's small in magnitude, it's less than 1 in magnitude, and it's negative. So it's some number between 0 and -1. Okay, so I'm actually raising x to a negative power. Okay, it's 1 over x raised to some power, right? And so what happens is x goes to infinity there. For this whole thing, it's going to 0. Okay, this now is k times 0, which is 0. Okay, and now we're done.